Hello everybody, this is going to be our first YouTube video asynchronous lesson that we're going to watch in our second unit on forces and fields. I've chosen this particular lesson because there's a strong mathematical component to this. The previous lesson we learned should have been Newton's first law, and just to do a quick recap on that, Newton's first law is the whole idea of inertia. I'll write that out here, inertia, where basically it states that an object that is moving is going to stay moving unless a unbalanced force acts upon it. And that really leads quite well into our second law. And so today's lesson is going to kind of work like this. We're going to do the asynchronous concept again, because I think there's a lot of value in that. Hopefully you guys do as well. The idea of pausing or rewinding or asking me for help, being able to go at your own pace. I think there's value to this. But the other reason why I want to do this is that Newton's second law actually involves a mathematical formula, which we're going to learn about in a few slides here. And so there's a little bit of theory to begin with. We're going to talk about relationships, but most of our examples are math examples. And so because kids sometimes need to go slower or quicker, then that gives you that flexibility. So let's begin. I'll erase inertia because I don't want you to think that Newton's second law has to do with inertia. Newton's second law is actually extrapolating on the idea of forces. And so let me recap inertia again, right? Inertia was objects are going to stay in motion unless an unbalanced force acts on them. Or really objects will not be in motion unless a force gets them moving. And so that's what this definition here is. A force is an action which changes the velocity of an object. And really, what is the definition of a change in velocity? Well, we call that an acceleration. We are very specifically talking about non-uniform motion now. We're talking about accelerated motion. If you have something that's traveling at constant speed, there's no forces involved because forces are what makes things change their speed. You may have heard the definition of a force being a push or a pull, and that's a pretty basic definition we give kids when they're learning about forces at first, but we have a better definition now. Now, Sir Isaac Newton, you've probably heard his name before. I would have discussed that on his first law. Sir Isaac Newton discovered there was a relationship. And there's a couple of relationships I need you guys to know about. One is known as the inverse relationship. And basically the way the inverse relationship works, it's like one of those old-fashioned seesaws. You know how those work? Where you have one kid on one side. So there's one kid on one side of the seesaw, and there's another kid on the other side. And in order for it to work, if one kid goes down, it means the other has to go up. That's known as an inverse relationship. And basically the way that works here in this is that Newton discovered that there's an inverse relationship between mass and acceleration. And this probably makes intuitive sense to you, because let's say that I asked you to try to accelerate a really heavy object. So let's say that we made the mass be really big, right? So hypothetically, let's say I asked you to throw a ball. But then I changed out the ball for you. Rather than it being a normal-sized volleyball, I made it a medicine ball, and I made the mass become increased. Well, there would be an inverse relationship that would cause the acceleration to decrease, because can you accelerate a medicine ball, a really heavy ball, quite as well when the mass goes up? Well, the answer would be no. It's harder to do, right? And the same thing applies kind of in the opposite direction. What if you decrease the mass, right? What if you made it so that rather than throwing the medicine ball, you were throwing something that had a lower mass, like a volleyball? Well, if I was trying to throw a volleyball, I have the ability to accelerate that mass more. And so that's this inverse relationship. One goes up, one goes down, just like the seesaw. And maybe another example of this might be, say you needed to push a vehicle. Now, let's say your friend got stuck in the snow, right? It's winter out, your friend gets stuck in the snow, and you need to try to push the car out, and you need to accelerate it, right? Because currently the velocity initial is 0, and you need to get it to a velocity final so that it actually moves, right? You therefore need to give this an acceleration, right? The difference between velocity initial and a velocity final would give it an acceleration. And so you're trying to push your friend out. Well, would you rather have to try to push your friend out who has a big half-ton pickup truck, or would you rather try to push the friend out who's driving a smart car? I mean, you shouldn't drive a smart car in the wintertime, probably. That might be a little bit more dangerous on the roads, especially if you don't have that safety aspect of having like of collision protection as much. But let's say you're trying to push a smart car out in the wintertime, it's going to be a lot easier to move the smart car because its mass is so low, right? But if you're trying to push out a big truck, and imagine the truck doesn't just have like, it's not just your normal half ton, but like there's a whole bunch of stuff in the back, right? Well, I think we all. So, okay, let's move on here. So that was known as the inverse relationship. But there's another relationship you should know as well, and that's known as a linear relationship. And you probably have already seen this before because we graph these in math according to the equation y equals mx plus b. And the way a linear relationship works is where if one thing goes up, well, the other one goes up. And I just discussed on the previous slide the idea here that if mass increases, acceleration has to go down, the reverse relationship. Well, there's actually a similar thing, but it has to do with force. If you have a force and an acceleration, the phrase that Newton used in his second law, he said the acceleration varies directly as the force. And so what that means is that if you use more force, you'd have more acceleration. If you can push harder, you'd get more acceleration out of it. Most people probably get that too, right? If you have more ability to push, you have more muscle, you're stronger, you'd have more acceleration. And so there is what's known as a direct relationship, which we sometimes use the word linear to describe that if this goes up, this also went up. If they both increase, you have a nice direct relationship. The inverse relationship is this one right here, though, where if you make your mass get bigger, you'll notice that the amount of acceleration is coming down. So now, graphically, we call this the linear graph. And for those of you who have done Math 20-1, you might recognize this graph. It's called the reciprocal graph. And the equation for the reciprocal graph is y equals 1 over x. Basically, the idea being if you make the bottom of this fraction, if you make x a bigger number, if you make the bottom of a fraction a bigger number, it actually makes y a smaller number. Let's just discuss why. If I give you 1 over 2, but then let's say I make the bottom of the fraction a bigger number, so it's not 1 over 2, it's now 1 over, say, 100. See how the bottom of the fraction became a bigger number? That's like this side right here increasing, because that would be your x value. Well, if you make the x value increase in a reciprocal relationship, it makes the y value that it was 1/2 a bigger number than 1/100th. And so that means your y value goes down. And so if you've done Math 20-1, you hopefully have seen this before. It actually means I can now go back and talk about what the slide, and I kind of skipped it. It basically states that the acceleration is proportional to 1 over m. And that's what this symbol right here means. Proportional. And so if you have a 1 over m relationship, which is like that reciprocal relationship, this is basically another way of trying to say the relationship is like 1 over x. It has that if one goes up, the other goes down. Now, hopefully that makes sense to you. Some of you will have more experience with this concept depending on what you've covered in math. If you're okay moving on, we will talk about this a lot more later. But if you want to ask a question about it, feel free to pause and ask me more about the direct versus inverse relationships. But basically, here's Newton's second law. What it states is you use more force, you get more acceleration. But if you use more mass, you get less acceleration, right? Push stronger, there'll be more of a change in velocity. But make it heavier, well, now you can't have as much change in velocity because it's heavier. Right? So it actually led to Newton's formula, and this is the reason why we're doing this lesson asynchronously, is that there is a formula we're going to work with today. It's fairly straightforward. It only has 3 variables. F net, I'll talk about that in a bit, but F stands for force, M and A, mass times acceleration. Now, the reason why we have to talk about this F net is that there could be multiple forces in play. For example, there could be a person pushing this way, but there could also be like a force opposing it that's not quite as strong. For example, let's say there was someone pushing this way at a value of 15 newtons, but someone was pushing back with a value of 10 newtons. Well, the net amount of force would be 5 newtons because it would be the difference between the two. And so there are times when we need to add to each other. There's times when we need to subtract from each other. This was a good example of subtracting from each other. There's other times though when you add, like for example, let's say I was pushing on a car with 10 newtons because a smart car got stuck in a rut because it was small and it was windy out and it was icy and it didn't have a whole lot of mass. It didn't hold a corner. Your smart car got stuck in the ditch, and so I'm pushing with 10 newtons, but my friend is also going to push with 10 newtons because we're both going to try to push the car. Well, in this case, since we're both pushing the back end of the car out of the ditch, now you're pushing with 20 newtons. And again, if I'm trying to push, and again, if this is a smart car which has a low mass, if I'm trying to accelerate this, I would rather have a low mass, because if I have a low mass, according to Newton's law, it means that I would be able to increase my acceleration if I have a consistent force. So anyways, that's our goal today. We want to work with this formula right here. And I'm defining the variables here for you. Hopefully you're familiar with forces already. We've discussed them a little bit in this course. You probably learned about them in Science 10. The unit for force is a Newton. Capital N stands for Newton. And its definition is how much force you need to make a 1 kilogram mass accelerate 1 meter per second, which is a meters per second squared. And this is very much the definition of physics principle number 1, accelerated motion. Only now what we're going to do is we're going to discuss in accelerated motion. We're not going to discuss, like, say, what it's doing as much. That's what we do in kinematics. In kinematics, we discuss, like, what it does, like what its time is, what its velocity is. We can still do that. But here we're more at the root cause of, like, well, why was it accelerating? And again, why is this thing accelerating? Due to a force. Someone pushed it or threw it or dropped it, or gravity was involved, or any other force that we learn about. So. Okay, so let's begin. Let's do some math examples. That's the reason why we're doing this asynchronously. So we're going to start with a fairly basic example. We're going to try to calculate the acceleration of a 1,250 kilogram car if we apply this much force. So again, imagine that someone gets stuck in the ditch. Would you rather be pushing out the smart car out of the ditch or the half-ton truck? Well, I'd rather be pushing the smart car out of the ditch because it's nowhere near as big. But I mean, these are the variables we're given, right? And so this is how much force we can use. So sometimes it's good just to write down your net variables. The force that we can work with is 3.51 times 10 to the 2 newtons. And sometimes I'll abbreviate in the little bottom corner here. I'll talk about what type of force there is. And so because it looks like we're probably like pushing this, sometimes you might see me write FAPP. And that stands for like the applied force, where someone is going to apply a force to move it forward. Sometimes we'll write things like, say, F. That could be, say, the force of friction. Fg can be the force of gravity. So we have different forces we can use, but for right now, I'll call this the force applied. The other thing we know is the mass of the vehicle. It's a 1,250 kilogram vehicle. This is a pretty basic question. We know that our net force is equal to mass times acceleration. And really in this example here, it appears we only have one force. So that must mean that our applied force is our only force. So we'll get to examples where you have to have more than one force. But for right now, we just need to solve for the acceleration. So I'm going to divide both sides by m and make F net over m equal my acceleration. And I mean, this is pretty basic. We're just going to plug in 351 times 10 to the 2. We're going to divide by 1250, and that'll give us our acceleration value. So I've calculated an acceleration value of 0.2808. So hopefully you've tried that as well. And that's not the right number of sig digs, unfortunately. So let's make it 2.81 times 10 to the minus 1. And the units for acceleration are meters per second squared. So that's how fast I have the ability to accelerate this car, this hypothetical car that got stuck in the ditch that we're trying to push out. So, okay, like I always say, if you got lost somewhere along the way, Pause the video, rewind, ask me to clarify. Otherwise, I'm going to kind of pause the wait time here. We'll just move forward, and we'll try another example. So here's a new scenario. This one's more of a vertical up and down scenario. Say we have an elevator. I'm even going to draw a bit of a picture here. Here's a box, because really, isn't an elevator basically a big box? And the reason why the elevator moves is because there's a big cable holding the top of the box, right? And so you and me, we're inside this elevator, and we are really hoping that the big cable that's holding the box up doesn't let us fall, right? And so sometimes we can call that a force, but another type of force we might describe is Ft. Now I'm going to pause for a second here and ask you to just maybe think for a second. What do you think that T stands for? All right? And so I'll kind of wait here for a bit. Consider, what do you think the T stands for? Okay. I mean, this is kind of weird because I'm not teaching you to the whole class, but the T we often use would be for the word tension. And the reason why we use that is because there's tension, right, in this cable holding it up and pulling it up. You ever heard that word tension before? Maybe another way of describing tension is something that does not have, like, slack. I was a water skier once. If any of you have water skied before, imagine that you've got a boat, right, and then behind the boat you have a rope, and then someone is trying to hold on to that rope while water skiing. That's pretty good picture there, right? Well, you want to have some tension in this rope because that's what's literally like the boat is pulling the rope, which is pulling you. But if the rope ever kind of dragged a little bit like this, what would end up happening is as the boat pulls forward, eventually the rope will become tight, and then you get a real big like yank. It jolts your arms. So maybe some of you kind of know this experience, and maybe it's not from water skiing, but maybe you know the concept of tension. We like to have our ropes usually fairly tight, especially if these ropes are holding up a big metal box that we're standing inside that we could like plummet down to our deaths, right? So we want tension in this rope. Anyways, that was my long way of kind of pointing out that this number right here, this 4.0 times 10 to the 4 Newton number, that we could describe as a tension. Okay, and it says that the elevator weighs 3,700 kilograms. And I just want to remind you that there's a formula that we can actually use to find a second force. Because why do we need a tension force holding us up? Well, if I were to draw this as like a free body diagram, hopefully you're familiar with the concept of the force of gravity. Now, this is a formula that's not only on your data sheet, it's also a formula from Science 10. And maybe we've discussed this already, but the force of gravity is equal to mass times gravity. Hopefully that's a formula you're familiar with. So the reason why I need to point this out in this video here is that we now actually have a net amount of force, because the tension in the rope is trying to keep us up, but gravity would make us want to fall down. Now, if I were to ask you which of these two vectors needs to be bigger, hopefully you'd agree that we want the tension vector to be bigger than the force of gravity vector, because if gravity wins in this fight, we're going to be falling downwards. So we definitely, if we're wanting to travel up, we would like there to be more tension than there is gravity. Right? So anyways, let's keep working forward in this problem. This effectively, by the way, is a free body diagram. We've discussed those before. And we're going to draw them a lot in this unit, the idea of a free body diagram, where we draw forces going other directions. Tension holding us up, gravity pulling us back. Now, we know our formula is F net equals ma, right? That's Newton's second law. But now I can write out a statement that says, really, we know what my F net is supposed to be. It's supposed to be tension subtract gravity. That's going to be equal to mass times acceleration. And I'm just going to move this out of the way. I'm going to try to move this a little bit out of the way here. Oh, apparently I can't. Okay, I'm just going to erase this. It's in the way. Let me rewrite this first. F, G, and that equaled mass times gravity. Okay, let's go back to this here. The reason why tension is subtracting gravity is because, well, we know this thing is going up, right? So the tension is going in the upward direction, but it's being pulled back by gravity. So that is where my net force came from, subtracting these two. Now, we were asked for the acceleration value, so I'm going to divide both sides by mass. And it's going to leave me with this formula here. the tension minus the gravity divided by the mass is going to equal your acceleration. And that's a pretty good formula, but we're still not quite all the way there yet, because as I look through the variables I have, mass, I even have tension, but I don't actually have the force of gravity written out yet, because I need to do another substitution. Remember how I said just a little while ago, hopefully remember this formula from Science 10, or maybe earlier in the course or in the unit I've mentioned this. The force of gravity can actually be written as mass times gravity. So here, this is the formula we need. By the way, some kids, sometimes they get to a spot like this and they say, Chris, can I cancel out the masses? But the reason why you can't cancel out the masses is that this force of tension doesn't involve a mass variable. If there was, you could factor and cancel out mass, but because this is a binomial on the top, you actually can't cancel mass. So here's how this formula is going to look then. Our tension was 4.0 times 10 to the 4. We are going to subtract the mass, which was 3,700, multiplied by gravity, and we know the effect of gravity on Earth is 9.81, and then we're going to divide that again by 3,700. This will tell me how much acceleration we have. So let's give that a try. 4 times 10 to the 4 minus 3,700 times 9.81, and then divide it all by 3,700 again. And I got an acceleration value of 1.00, I guess. Yeah, actually only one sig dig. 1.0, we'll get rid of that one. Meters per second squared. I just want to double check the math there, just make sure I didn't make a mistake. 3,700 times by 9.81. Yeah, and then we're taking 40,000 and we are subtracting that number. And then we're dividing by 3,700. Yeah, it's basically one right on the dot. I just want to double check because it's pretty rare that you get a calculation that comes out right to an even number like that, but it looks like the math holds there. So I'm just going to erase it so that we have the right number of sig digs written nicely here. Let's just go back to the red pen here. And so there we go. We now know the acceleration. This elevator is accelerating upwards at a value of 1 meters per second. Now, one of the things I want to point out here is that this involved a lot of substitutions and rearranging of formulas, right? And it really first involved starting with Newton's second law. And then I rearranged by putting in the net force amount. So I subtracted those. And I divided by mass on both sides. And then I changed out the Fg for the mg. Now, the reason why I want to point this out, I'm just going to erase all the stuff I put on there, is that it would be fine by me if you went right from this step to this step, because I kind of did everything in little pieces. But if you understand that F net was Ft minus Fg, but you knew that Fg was mg, and you knew you had to divide both sides by m, if you just wanted to skip this step here and skip this step right here, that's actually sufficient in terms of one of the expectations. You're asked to, on a written response question, show an initial formula, show any rearranging you do. You have to show this step right here. This is the step known as substituting. This is where you substitute variables with values. And so, yeah, but if you want to skip some of the middle steps there as we do some rearranging of algebra, I don't need you to show me every little piece there. So, okay, I want to move on here because I got more examples. Like always, if you have questions, pause and ask me for some help. Otherwise, let's try another one here. Similar question, but now it wants to know the acceleration if the tension in the lift cable is reduced to 3.3 times 10 to the 4. So I want to draw kind of the exact same scenario here. So I want to draw a free body diagram. We know that gravity is pulling us down and tension is pulling us up, right? So there's a rope with tension on it pulling us up, and gravity is pulling us down. And we actually know the gravitational force. We could actually calculate it. I know I did it all in one step in the last example, but I could take that mass, which was 3,700, and I could multiply by 9.81. And I could actually just calculate just how much the force of gravity was. So 3,700 times by 9.81 gives me a value of 3,6297 newtons. Well, hang on a sec here. The force of tension is only 3.3 times 10 to the 4. which means if I kind of wrote that out, it would be 33000 because I'm adding 4 more decimal places. What's different about this example here? Just going to pause for a second so you can kind of think about that. What's different about this example here? And hopefully you came to the conclusion. The force of gravity is now greater. So this is an elevator that is going down. Now, we would not want to leave the elevator in this state for very long, because if you had gravity and tension like this elevator is going to start to accelerate downwards. And we don't mind it accelerating downwards a little bit, but then we'd like to go at a constant speed. We don't want it to keep speeding up, right? The way an elevator is supposed to work is it's supposed to accelerate you at first, and then it's supposed to recalibrate itself and make it so that the two forces are equal to each other. And so once it gets in motion through an acceleration, then you want to make the tension and the gravity equal to each other, and that way it just keeps going the same speed the whole time. So if we don't change things and make the tension get increased very quickly, this elevator is going to start accelerating, and it's going to start accelerating in a downwards direction. It won't be accelerating as fast as 9.81 gravity normally does, but it's still enough that, yeah, it could be concerning. So anyways, let's solve this one here. We're now going to change the equation and say that it's actually Fg minus Ft. That's equal to m times a. And the only reason why I'm flipping this is as I try to find that net force there, I now know that gravity is bigger than tension, right? Because I just looked those numbers up. And so I'm still trying to solve for the acceleration, so I'll divide both sides by mass. And maybe I can actually go right into the substitution step now. I know that the force of gravity is going to be 36297. I know the force of tension is 33000. And I know the mass of the object is 3700. So I could solve for acceleration now. And I mean, I showed this in a slightly different way than I solved the last example, which is fine. There are different ways of showing. One of my personal preferences is to try to do all of the work algebraically by rearranging formulas that still have all the letters there, and then in the last step, typing in numbers. And one of the reasons I prefer that is that it reduces the chances of you making rounding errors. But hopefully you'll get this value right here. I got 0.89 meters per second squared. And I'm going to point out that this is now going down, which means that we're now accelerating in a downwards direction. Now, it's only about 1/10 as big as what gravity normally does, so it's not a huge acceleration rate. That being said, if this was happening over, say, like a big building, like a building that had, like, say, 50 floors, well, if you kept accelerating at this rate every second, you'd start hitting a pretty fast speed, and that would become a problem. So hopefully what I'm saying here makes sense, is that this acceleration, you only want it to happen to get the elevator moving up and down. Once you get the elevator in motion with this acceleration, then what you'd like to do is you'd like to make both forces exactly the same, so that whatever amount of tension going up is the same as what's going down. If that happens, you no longer have acceleration. However, as we learned last day, if an object is in motion, it will stay in motion unless an unbalanced force acts on it. So once the elevator gets moving, it will stay moving. This is really similar to that rugby scrum example I should have shown you, where if there's someone pushing from the back and pushing from the front, if there's equal forces going in opposite directions, but the thing is already in motion, or the rugby players are already in motion, they will stay in motion until there's an unbalanced force. And so let's say that you then need to stop this elevator. Well, then you make tension bigger than gravity for a bit, and then the upward acceleration happens. So, okay, hopefully again that made sense. Like always, pause and ask questions, but I'm going to try another example. Now, this is a pretty classic example. It's the idea of actually having two objects tied to each other by a string. And this kind of changes your free body diagram, because what ends up happening is you actually have two objects, and sometimes you like to consider them as like one big system. Sometimes we just pretend that they're all one big object. We could pretend that this thing right here is just 30 kilograms and they're all stuck together. And that's one possibility. But another way that you can consider it is two individual free body diagrams. You could consider, for example,
that this object right here is being pulled by a string. And this string has some tension on it that's pulling it. Whereas this 5 kilogram object, it's actually getting pulled backwards by some tension because it's really being held by the same string, but it's being pulled forward by what looks like an applied force because an applied force is pulling it this way. So in theory, you could actually consider these things to be separate. And we're going to do questions like that in tomorrow's lesson. However, for today's lesson, I actually bolded the word here. I want to consider it to be the system. And so even though there are two boxes being pulled this way by an applied force, what I think is going to work better for this particular example is just to treat them as though they're one big box with a total mass of 30 kilograms. So let's draw that as a free body diagram. We now have a 30 kilogram object, and it's effectively being pulled by an applied force. And that's really all that we've got right here, except as I read here, it said there were some frictional forces. And so if you're pulling the box towards our right, it would make sense that the frictional forces are trying to oppose it. And again, we're treating the whole 25 and 5 kilogram, both boxes, we're just pretending they're just one big box. So I know there's a string in between them, but like pretend there's no string, pretend that they're glued together, right? Okay, so now you have, two different boxes. I know the shape is a little different, so maybe it looks more like this, right? And these two boxes here, they've now been attached by glue, but I mean, they're just one big system, right? So the process works the same way. Your net force is equal to mass times acceleration. And this is why it's often good to draw out those free body diagrams, because it kind of gets you going. So our net force will be the applied force minus friction. And I want to pause there for a second, because my question here is, why do we know it was applied force minus friction? Why wasn't it friction minus the applied force? And the rationale here is that if friction was larger than the applied force, you'd be going backwards, right? Like if somehow friction was bigger than the applied force, these boxes would be going backwards, but friction doesn't work that way. Friction can never be more than the applied force happens to be. Otherwise, objects that are just sitting there resting due to friction, they would start moving because of friction, and that's not how friction works. So hopefully that's a good explanation as to why, but like it seems to be that we're moving in this direction right here, and we're moving because of the applied force, not because of friction. Friction can't cause something to move. Friction opposes the movement of objects. And I believe we actually have an entire lesson that we're going to discuss friction some more. So anyways, let's solve this one. We're actually being asked to solve for the applied force. So to do that, I'm going to add the force of friction to both sides, making this new equation. The applied force will be equal to mass times acceleration plus the frictional force. And if that made sense to you, then I'm just going to start plugging in numbers because I have them all. The total mass of the system was 30, and it told me in the blurb above they were accelerating at a rate of 2.75. And it told me that the frictional forces was 250. Now, this is a good time to talk about why on this side of the equation it was being subtracted, but then when you added FF to both sides to like solve it algebraically, hopefully this kind of makes logical sense, is that you got to figure out how much mass and acceleration you have, but then you're going to need more applied force because you need more to make up for your frictional forces. This is another good way of describing that linear relationship. If you have more frictional force, you're going to need more applied force to make up for it. So like if there was no friction, you just take 30 n times by 2.75. But because there is a frictional force, there's a direct relationship. If you add more friction, you're going to need to have more of an applied force to make up for it, and there would be a nice direct relationship. So I need to add 250. So anyways, long story short, I'm kind of stalling to give you time to try the math here. 30 times 2.75 plus 250 gives me a total applied force of 332.5. And if you left it there, you really shouldn't earn full marks because there's two things that are incorrect, and I've talked about these before. The first one is sig digs. We're going to have to round this to 333, it appears, because it looks like I get 3 sig digs. Now, some kids might say, hang on, Chris, this 5 kilograms right here, that looks like it only has 2 sig digs. But I need to point out a rule that maybe I mentioned in class to you, maybe another teacher's taught you, but if you ever take 25.0 kilograms and add it to 5.0 kilograms, this is a good discussion of precision. Both of these numbers were precise to the nearest tenth, which means when you add them, they still need to remain precise to the nearest tenth, and so therefore there actually is 3 sig digs. One used was 30 kilograms total, so that has 3 sig digs. This one had 3 sig digs, this had 3 sig digs. So let's make it 333 newtons, and I should even give it a direction. Let's say that we were pulling to the right, because it sure looks like in this diagram we're being pulled to the right. So, okay, pause, rewind, ask me questions. Otherwise, let's try next example. This is known as a pulley example, and maybe I've shown you one before, maybe you've done one in your assignment already, but this is another classic example where we're going to have something wrapped over a pulley. And this is kind of similar to what I was suggesting in the previous example, where there's a string or a wire attaching them. And so in a way, this box right here, what it has happening to it is it's getting pulled down by the force of gravity. And this box is also getting pulled down by the force of gravity. But what's kind of cool here is that they're being connected by a string, and that string is tension. And so this box is being pulled up by an amount of tension, and this box right here is also being pulled up by the exact same amount of tension. And so even though this is kind of in a vertical up and down scenario, if you kind of imagine that you were straightening this out, if I were to draw the free body diagram for these boxes just in like a straight line, what you really have is a force pulling this way on, say, the 12 kilogram box, and that would be, say, the force of gravity. And I know it's actually pulling down, but just imagine that I just straighten this out for a bit. Then this guy right here is being pulled the opposite way by some tension, because this string is clearly going to have some tension in it. Well, the other box also has some tension on it, and it's being pulled the other way by a force of gravity. And this is the 5 kilogram box. Now, we can actually do the exact same thing we did in the last example. We can just kind of pretend that really all of this is just one big system. And so what you really have then is just one big tied together blob, which weighs, oh, I think I wrote down the mass wrong. It looks like the total mass will be 19.50 kilograms. But really, if you consider it like this, even though this rope is being pulled up by tension, this one's also being pulled up by the same tension in the same rope. And so really there's only 2 forces occurring. One force of gravity here, one force of gravity here. Which one's bigger though? Well, isn't the one on the 12 kilogram box going to be a bigger vector than the one on the 7.5 kilogram box? Because we know that the force of gravity is mass times gravity. And so if you have more mass, you'd have more force. That's another direct relationship. If I were to draw a little graph here, if you have more mass, it means you would have more force of gravity. Gravity makes more of a force. Doesn't that actually make sense though? Let's say I were to drop a pencil on my foot, and then I was to drop a bowling ball on my foot. They're both going to be accelerated at the same rate, because gravity is going to make them move at the same speed. But a bowling ball could cause a fracture in my foot, whereas a pen wouldn't, because a bowling ball has a high mass. So again, there's a direct relationship between mass and gravity. Make it a heavier object, there's more force to it. It's not traveling faster, but it is going to provide more of an oomph when it hits you. All right, anyways, let's get back to this question here. It says it wants to find the total length of time it's going to take the box to hit the ground. I've thrown in like a little bit of a twist here, because if we're looking for the amount of time it's going to take the ground, we're actually back to kinematics. And it actually mentions that the 12 kilogram box is 8 meters above the ground. So we actually know a distance in the y direction this has to travel. It has to travel 8 meters. Now, if we kind of consider the kinematics perspective, we still need to know some more variables. And normally in kinematics we could know the acceleration, because the acceleration would be gravity. But we're actually going to calculate the acceleration in this example by using Newton's law, because it won't be quite 9.81 anymore, because there's a counterweight. If there was no 7.5 kilogram object here, yeah, this thing would fall as a projectile, but this isn't a projectile anymore, because there's a counterweight on the other side, making it so that gravity won't pull it down quite so fast. So there's kind of a two-step process here. We're going to take this formula here and do F net over m, and we're going to calculate the acceleration that way. And so I can actually find the acceleration by doing the F net divided by my mass. So there we go. We've now got two variables. At least we will have two variables to solve for time. The final variable is that it said velocity initial was 0. So I believe we now have enough information to begin solving this puzzle. I'm going to start by working backwards. I'm going to consider what variables we learned about in our kinematics unit that fit this formula. And this formula from kinematics will be d equals vit plus 1/2 at squared. And I'm going to rearrange this formula for time. And because velocity initial is nothing, we've done this enough times before, this whole bit right here cancels. And so to solve for time, it's going to be 2 times d divided by a, all square rooted. That'll give you time. However, we don't actually know a. We know the distance it's going to travel, but we don't know the acceleration. So I'm going to work over here for a bit. I said we could find the acceleration by finding the F net over m, but the F net is really going to be the force of gravity for one of the objects minus the force of gravity for the other object. That'll be our net force, because really this blue object is going to have a higher force of gravity than the other one over here. And if I were to kind of keep writing out formulas, this would be mg for, say, the first object, and we'd have to subtract mg for the second object, and that'll be equal to acceleration, but again I still have to divide by mass. And this is where things get a little confusing, because you look at this and you go, hang on, can't I cancel these masses? Well, actually all these masses are different. This mass is the 12 kilogram mass. This mass right here is the 7.50 kilogram mass. But you know what this last mass is right here? It's the mass when we treated this as one big system here. Right? This force of gravity is based just purely on the blue box. And so it's going to be mass times gravity for the blue item. So it's going to be the 12 kilograms goes in this direction. And the 7.501 will be the mass times gravity here. But we glued this all together and treated it as one big system. So the mass that we're going to use down here is going to be like the total mass, which is going to be 19.50. So I'm going to have to be very careful that I use each individual mass in the right location. So I'm now ready to kind of blur this together. First, I think I'm going to calculate my acceleration. So I'm going to work with this now. Let's see if I can kind of draw it off to the side here. I'm going to go 12 times 9.81, and then I'm going to minus 750 times 9.81, and I'm going to divide that all by the total mass of 19.50, and this will give me my acceleration. And so while I'm doing the math for this, if you're lost as to why I'm putting 3 different masses in those locations, can you pause the video and call me over and have me try to explain better as to why we did that? But I've now calculated my acceleration. It is 2.26 repeating. And I'm going to store that as letter A in my calculator, because I know I need to use that value again. So unless I made a mistake typing in values, I now know letter A. Let me just check one more time. 12 times 9.81 minus 7.50 times 9.81. That's the difference in my gravity amounts. And then I divided that by the total mass of the system. Yeah, I got 2.2. Was it 19.50? Yeah, 19.50. Oh, I realized I think I wrote this down wrong. Oh. So I'm just checking the math in my calculator one more time. I don't want to make any mistakes here. Hopefully you guys can do the same thing. 19.50. Yeah, 2.26. Okay, so this number has now been stored as A in my calculator. Well, now that I have the acceleration value, now I can go and plug these numbers in. So to solve for the amount of time it's going to take, we're now back to doing kinematics. It's going to be 2 times the distance, which was 8 meters. And then I'll divide by the acceleration value I just found. Now I got to point out, the normal acceleration due to gravity is 9.81, but due to that counterweight on the other side, it's only going to be 2.26. Any of you who maybe have experience working in theater, I understand that sometimes like theaters will use counterweights as a way of trying to like drop or raise props, as like a stage hands would use that, right? And so you need to drop this object right here down to the ground, but you don't want it to crash down to the ground with a lot of force. So you put a counterweight on the other side so that it will fall down, but it's not going to fall down with gravity's acceleration. It's going to fall down with an acceleration of say 2.26. So, okay, anyways, let's get to the final answer here. Let's move forward. 2 times 8 divided by letter A. And then if I square root the whole answer, I get a final time value. I got 2.658. And as I look at the sig digs that I used, now you know the last time I did this, I had to add these two numbers, the two boxes together. But it looks like actually what's going to limit me today is the 8 meters above the ground. So 2 sig digs, I'm going to get 2.7 seconds. It was actually 2.65, but that rounds up. So. Okay, same as always. If you have questions, pause, rewind. Maybe you're speeding up. Maybe I'm going too slow. I do that too sometimes. Maybe for some of you this is too slow when you're on fast forward. So, do I have one more example? Yes, I do have another example. I've got to do the inclined plane examples. Okay, got to speed things up here. Another thing that we often do is what's known as the inclined plane examples, where what we have is a box that's kind of on an angle. This is known as the inclined plane. And what's weird about this one here is that even though this is on the angle, sometimes what you'd like to do is kind of like twist it like this. I want to start from scratch though and make sure that you understand what's happening here. There's actually 3 forces that could be in play as there's an object on what's known as the inclined plane. Gravity always goes down to the center of the Earth. And we've hopefully already discussed the idea of a normal force. A normal force always goes perpendicular to a surface. And so since this thing is resting on a surface, there's some normal force. But if this thing has the tendency to go down the hill that way, there's also something known as a frictional force, which would oppose it. And so we could draw a diagram that looks like this, where there's actually multiple forces in play in different dimensions. There's like the y and the x dimension that we have to deal with. But like I just kind of twisted the diagram a bit here, sometimes it's better to kind of turn this sideways. And so even though we know that this is not actually how this looks, now maybe I can see my y and my x dimensions a bit better. Because the force of friction is happening in the x dimension, the normal force is happening in the y dimension, and gravity is actually happening in 2 dimensions. Part of it is a y component, and part of it is an x component. And I can actually calculate the force of gravity in both x and y. And so if you can kind of imagine turning it sideways, that's how we're going to solve some of our next problems. So let's do some examples now. Let's say we put a box on an incline of 30 degrees. So the incline right here is 30 degrees, and there's a box on this incline. But it says it remains stationary. You know, that's a really big hint here, because it means that your F net must be 0. For it to remain stationary, whatever frictional force we have right here, that's kind of like keeping it from sliding down the hill, must be the same as whatever would want it to cause it to go downhill. But then the question is, well, what would cause it to go downhill? Well, don't forget, when we drew this diagram on the previous slide, there's a normal force going this way, but there's a gravitational force pulling it straight down. Now, this is probably one of the times where you're going to want to ask me to clarify, because the first time you see one of these, it's a little confusing. Now, there really is no force, though, right here. You know where that force really is is if I were to use some different colors here. This force of gravity should really get broken up into the force of gravity in the y direction and the force of gravity in the x direction. And I know it seems like, hang on, Chris, none of this is in the x and y direction, but that's because this whole mess right here, if I were to like try to combine this all, I think there's a way of doing this here. We need to group these. If I were to group all these together, you gotta treat this whole diagram as though it's been tilted. And now maybe you can see that we have two x direction forces. The force of friction is in the x direction. And the force of gravity that's kind of pulling it downhill, it's also in the x direction. And so if I were to draw a free body diagram, there's actually going to be a force of friction pulling a box this way. There's a force of gravity in the x direction, which seems weird because hang on, why is gravity in the x direction? But it's only because it's on an incline. These two forces better be equal. But here's the other cool thing. The force of gravity in the y direction is going to need to be equal to the normal force. And if these two things weren't equal to each other, then the box would do one of two things. It would either start falling through the ramp, meaning the ramp broke, or it means it would start floating upwards, which would really not make sense. But we would actually have to have balance in all four directions, really in both the x and y dimensions. Now, tilting this every single time gets a little tedious to try to tilt this picture every time. So you just have to be able to like change your perspective and just recognize that x and y is now in a different plane of reference. Really, this is now my x plane of reference, and this is now my y plane of reference, and just kind of tip your head. Now, in terms of solving this, we then need to know this angle right here in order to actually calculate FG in the y direction and FG in the x direction. We need to know this angle right here. And to do that, to find that angle here, there's a lot of trigonometry involved, but basically the logic behind it is that there's a right angle right here, which makes this 60 degrees. But there's also a right angle right there, which means if this part is 60, then this remaining angle is 30. So the cool thing is we actually know this angle right here is 30. Whatever angle right here is actually the angle there. And so I'm now actually ready to kind of show you how we're going to solve this equation. We know that our F net needed to be 0. There needs to be no net force in our x direction, which really means that my frictional force needs to be equal to my Fg in the x direction. Oh, I almost drew that wrong. Fg in the x direction. But I know what Fg in the x direction is. We've done this a few times before. It's going to be whatever the hypotenuse is, which will be mass times gravity, because this side right here is the force of gravity. It'll be mass times gravity times the sine of theta. And the reason why it's going to be times the sine of theta is because this is the opposite side, this is the adjacent side, and this side right here is the hypotenuse. In what I'm drawing in green right now, I should really use another color here. Let's use a different color just to make this be really clear. Let's use pink, fuchsia pink. There is a right angled triangle right here. And this side over here is your hypotenuse. This side over here is your adjacent. This side is your opposite. So whenever you're looking for the FG that's in the x direction, you're going to use sine. And whenever you're looking for the FG in the adjacent direction, you'll be using cosine. So yeah, this is a big leap right here. This is where you're going to want to pause. This is why I'm making this video be asynchronous, because often kids, they get really lost in class when I do this for the first time. But if you understand, here's going to be our answer. It's going to be 15 times 9.81 times the sine of 30. That will be how much friction is needed to make this box be at rest. So it'll be 15 times 9.81 times the sine of 30. And so the final amount of force I have with sig digs, 2 sig digs, is going to be 74 newtons. Now, if that made sense to you, that's awesome, because this is a challenging section we just got to right here. So maybe rewind the video, put your hand up, ask me for help. But if that made sense, we're going to move on and try. I've got 2 more examples here. On this next example right here, we've got the exact same scenario. So hopefully by repetition this will make sense. We've got our inclined plane. And so the inclined plane is 28.5 degrees right here. And again, we have a box sitting on it. And I'm actually going to tell you how much friction we have this time. It's being pulled back by 3 newtons of friction. And that's all I'm given in terms of forces. But we know there's more. We know that there is a normal force right here. And we also know that there is gravity pulling down. Now, I should really write gravity on the other side here, because I want to set a good standard here. Now, if you kind of tilt your head to the side again, though, what we really have to calculate, though, is the force of gravity in the y direction and the force of gravity in the x direction. Because keep in mind, you got to tilt your head. This plane is the x direction, and this plane is the y direction. And so what I know is that if I'm going to calculate my net force in the x direction, it's going to be the force of gravity in the x direction minus the force of friction. Well, the same logic still applies to what we just did in the last example. This angle up in here in the corner will be 28.5 degrees. Every single time, if I give you an angle right here, you can automatically put it right up here in this section there. And if that makes sense as to why, that's fantastic. Ask me to show you again if it didn't make sense the first time. But I'm going to kind of keep piecing together my formulas. My F net in the x direction will be the x component of gravity minus friction from pulling me back. And that's equal to mass times acceleration. We've been asked to solve for acceleration, so I'm going to divide both sides by mass and make myself a new equation, which is that the Fg in the x direction minus the force of friction, all divided by the mass. There's my acceleration. Now I have many of these numbers, but what I don't have is Fgx. But again, if you understand your trigonometry, your Fgx is going to be Fg times the sine of theta, because it's going to be the opposite compared to the hypotenuse. We've done this many times before in the previous unit. And so if you need me to give you the refresher as to how I made that triangle work, but since this side is the opposite side, it's going to be this force on one side as the hypotenuse. This side is the opposite. And so that's how we're going to find Fgx. It'll be Fg sine theta. But we know what Fg is. It's actually mg. So piecing this all together, Fgx will actually be mg sine theta. We'll then minus ff and divide by mass. And as a brief aside, once you get the hang of it, I can tell you that Fg in the x direction will always be mg sine theta. It always is, I promise. And Fg in the y direction is always mg cos theta. Now, while we're doing this for the first couple of times, I'll try to explain why that is. But after a while, we're just going to kind of want to skip ahead to the shortcut version. So, now, one more thought here. Some kids might say, hey, we can cancel mass. But again, no, we can't, because this ff here doesn't involve a mass. It's a binomial on the top. So, we're basically done. We just need to plug in our values. So I'm going to start plugging in numbers. It's going to be 5 times 9.81 times the sine of 28.5 degrees. We're then going to minus the force of friction, which is 3 newtons, and divide by our mass again, which was 5. And so at this point, it's just calculator typing in. If you understand the big picture of how we put this together, then hopefully you can just do the math typing. So I calculated an acceleration of, it's basically 4.08, and it looks like I get 2 sig digs, so it's actually 4.1 meters per second squared. And the direction of that is going to be, I'm actually just going to draw an arrow for the direction. It's going to be down the hill, which is kind of what we defined as our x direction, but that'll be our acceleration. Oh, that's a hard example. There's a lot of theory to understand how to solve this, most specifically in regards to this triangle right here and understanding those forces involved. It is very, very similar to the concepts we used in our kinematics unit where we had triangles for vectors, and this was the hypotenuse. And we say had to find the velocity in y and the velocity in x. Remember how we had to do that? And this was always equal to the hypotenuse times the sine of theta, and this was equal to the hypotenuse times the cosine of theta, if this is your angle. We did this back when we were doing our projectiles lab. It's very similar. It's just this triangle here has been rotated, and it's kind of flipped around a bit. Okay, I've got one last example we're going to do, then we're going to call her quits. This example kind of combines a few extra things in, because I'm actually going to give you a distance and a time. And I'm also going to tell you that something begins at rest. And I'm not even looking at the rest of the question here. I'm just telling you that it begins at rest, slides, and has a time value. Hopefully that's kind of a dead giveaway that if I give you a velocity initial of 0, a distance of 14.5 meters, and a time of 6.25 seconds, we should be able to solve for an acceleration. Now, you might say, Chris, how did you know we have to solve for an acceleration? But you're going to start to recognize that acceleration is the key link. Acceleration is found in both kinematics, which was our first unit, but it's also found in dynamics, because it's also found in the one formula we've been working on today, F equals ma, F net equals ma, really. So if we can find the acceleration by using a kinematics formula, we can actually plug it into this formula here. So first I'm going to find that acceleration. I'm going to use a kinematics formula, d equals vit plus 1/2 at squared. Velocity initial is nothing. I'm going to get rid of it. And to solve for the acceleration, it's going to be 2 times d divided by t squared. That'll be my acceleration. And I think I'll just leave that for now. I'll plug in numbers later. I can work with that. Maybe. Actually, no, let's find that number. I take it back. Let's find that number. 2 times 14.5 all over 6.25 squared. Let's find that value. 2 times 14.5. Apparently I'm changing screens on you, sorry. Divided by 6.25 squared. And I now have an acceleration value of 0.7424. And I'm going to store that as letter A because I know I'm using that again later. Okay, now let's talk about the actual diagram itself. It's the same thing we've been doing for the last 2 examples. We have a box, only it's not a box, it's a snowboarder, but it's the same concept. And the snowboarder is going to be getting pulled backwards by friction, but the only reason why it's going down the hill is because gravity pulls straight down, but if you calculate the components of gravity, the component that we want is the Fg in the x direction, which we hopefully now have memorized is mg sine theta. And so if I start to put together some formulas here, I'm just going to make the page bigger. We know that F net equals mass times acceleration. And our 2 forces in play are going to be the mg sine theta force, which is the downward force that pulls you down the hill. It's the portion of gravity that pulls you downhill. Some of the gravity pulls you into the mountain, some of the gravity pulls you down the hill. So it's that portion there. But then we have to subtract off the frictional forces to get mass times acceleration. And this question here says find the frictional force. So we're nearly there. I'm just going to do some algebra. To get the frictional force by itself, I'm going to play a cool little trick. I'm actually going to add FF to both sides. And the reason I did that is that now I don't have a negative FF anymore. I now have FF over here on this side. And instead, I'm going to bring mass times acceleration to the other side. And it's going to give me this formula when I'm done. mg sine theta, that's a theta, not an h. And we're going to minus the mass times acceleration. And there, I now have a formula for my frictional force. Again, if I lose you on a step like that, call me over. But now we have all the variables we need. Let's plug them in. The mass of the snowboarder, ooh, there was a trick here. Look at this, this is sneaky. They gave us the gravitational force of the snowboarder was 850 newtons, which means if the gravitational force was 850 newtons, you know how that's equal to mg? But g is gravity, right? 9.81. If I want to find the mass of the snowboarder, I have to take 850 and divide both sides by 9.81. That was kind of a sneaky little trick I played there. I just wanted to show you that. We can actually find the mass of the snowboarder. It's actually 850 divided by 9.81. So the snowboarder's mass is actually 86.6 kilograms. I'm going to store that as letter B. Let me explain that one more time here. In the question above, it didn't give you the mass of the snowboarder. It gave you their force of gravity. But if you know their force of gravity, remember how force of gravity is mass times gravity? If you want their mass, then just divide both sides by 9.81. That's how I got the mass. So this is going to be letter B times by 9.81. So I mean, I guess really this right here is really 850. Then we're going to times by sine of my angle. And the angle was 35 degrees. And then I'm going to subtract the mass, which was B. And then the acceleration we found earlier today, we made that letter A. So we're basically done. We just need to do all the calculation typing. B times 9.81 times by the sine of 35. And then we're going to subtract whatever letter B is times letter A is. And so I have a final answer of 423 with sig digs. It looks like I only get 2 sig digs, eh? 35 degrees limits me to 2 sig digs. So this is going to be 4.2 times 10 to the 2 newtons, because this is a force of friction we just solved for. Oh my goodness, that is a long lesson. This is one of the reasons why I do this asynchronously, is that if I taught this lesson to the whole class together, the run time right now is 1 hour and 5 minutes, which this is going to take all class to do. The nice thing about doing this asynchronously is that if I lost you at some point, and it's likely that that could have happened, it is okay if that happens. Because I did this asynchronously, you can pause, you can rewind, you can go at your own pace. You can watch this again later. You can do it in different seatings, right? But if I did this all together in one big hour-long lesson in class, there's a good chance that you might have tuned out halfway. But doing this asynchronously hopefully had some value. So, okay, that's it for my lesson. Make sure you ask me questions. I imagine you have some. This is often one of the lessons that confuses kids. So make sure you ask me some questions, and we'll chat soon. So thanks everybody.